Right. Little experiment on my bench, streaming from the bench. And numerous projects I want to do. One of them is a lag tester, latency tester, to be able to very easily measure latency between the input device on a controller on a video game and the response on the screen. So this could be quite interesting, because it's not enough that I want to be able to test the input lag on a particular monitor, for example, but I want to test the lag on actual video games. Just bear with me a moment. So how to create a generic lag tester that will test a video game in situ to measure the amount of lag. Actually, the easiest way to do that is probably to use a high-speed camera, or even just any camera these days on your phone will be able to run at a fast enough frame rate for you to make a measurement. But I thought it would be fun or cool to make a self-contained device that could do it, and it would actually be useful, because I often ask myself the question, what is the lag? So one of the possibilities is to create something that could be attached to a device with maybe not this many digits. Just one of these would be good enough. That would be able to show up to 9-second lag, which given trends in the video game industry, we could be there quite soon. But that could show the number of milliseconds. And so then there's the question of how to measure it. And I've actually done an experiment on this before, where what I did, this was for Kickoff Revival actually. I was playing Kickoff Revival on the PS4 while I was developing it. It was written in Unity on the PS4, and there was something was really bugging me. I deliberately bought a monitor with a low input lag so that I would have a good reference. But I was noticing that when I was playing on the PS4, the controls felt soupy. It was like it didn't feel responsive. And so I was going, what is the lag? I needed to measure the lag from the controller through to a change on the screen. So what I did was set up a very simple circuit, not this. And this actually worked quite well, and I used this in order to test lag on Kickoff Revival. But it'd be nice to have something that worked, that was more sort of general. But what I did was, it was such a stupidly simple idea. Now I had, of course, the ability to change what the code did, because I was doing development on the console. So if you had your controller here, whatever, and what I would do is have a button. When you smash the button here, and I use the word smash for a good reason, when you press the button here, it would cause the screen to go from black to white. And so, yeah, this was set up in a Unity scene, very simple, few lines of code. You press the button, changes the display from black to white. And then what I did was I made a little device that used a photoelectric sensor. I've got one. Maybe I've got one to show. One lying around, but they look like this, more or less. This is actually a condenser microphone. More about that in a moment. But what I did was, they look a bit like that. So what it does, what a photoelectric cell does, is it changes its resistance according to the amount of light that's shining on it. And I set up a circuit so that with a 555 timer, so that when the light either shone or not shone, it doesn't matter which, on it, it would make a noise, a tone, and go me. Simple as that. Me. And then I got a microphone. So what we got then, that photo sensor I put on the screen. So now when the color the color on the screen changed, it would either play the tone or not play the tone. Okay, and then what I did was I took a microphone, and this was connected to just, you know, Audacity on a computer, and all I did was smash this button, and when I smashed the button, it would cause the screen to change its color, and the changing color from white to black of the point where the photocell was would cause the tone to begin or stop. I can't remember which I did. It was one or the other. It was probably stop. Doesn't matter. So the point then is I would record that audio, and then what you can do is you can go and look at the audio. And when I looked at the audio, what did I see? A big, like this. It would then do a big thing here where I had hit the button, because the microphone would pick up me smashing the button. So this way I got the timing of when the button was pressed. And then this would change the color here, and then we would get the tone. And all I needed to do was measure the time between these two, and this gave me the lag. Now, I was quite pleased with this result because I was able to do it with virtually no really complexity, and just using stuff, you know, just audio sampling, but it's entirely reliable, because there's no way this can go wrong. You record, you hear when the button is hit, and so the moment you see a deflection in here, you know that the sound of the button being hit has been registered, and then it would go through and the tone would change. Now, some of you know about photoelectric cells will know that, and there is one, because there's a bit of a question mark with this idea, photoelectric cells do not have an instantaneous response time, right? However, there is a response time. There's a curve that gets generated as there is a change. So there is a lag inside the cell. But if you are looking at this, you can see when it starts changing, when the amplitude of the signal starts. Might do this, and you can see quite clearly where it began. So this allows you to be quite accurate about the timing of when the photoelectric cell was influenced by the light on the screen. And since the sample rate, even at CD audio, is 44.1 kilohertz, there are 44,000 samples a second. So that gets down to well under 1 millisecond. It's well, close to a 50th of a millisecond, isn't it? Or something like that, 20th of a millisecond. Something in that order. It goes way, way below 1 millisecond. 1 millisecond accuracy is actually quite good. So although it sounds like it was, you know, it actually worked. And from this, I was able to find that Kickoff Revival had a lag of around 100 milliseconds in total. So this is the round trip for going through the input device through to the engine, being rendered, being pushed out to the monitor, which then has its own lag. You add this all together and you ended up with around 100 milliseconds, which is appalling. It is terrible. So I fixed it. because Kickoff Revival did not ship with this lag. So how I did that is to do with the way that Unity worked. But one thing, a tip, if you're a Unity developer and you're really concerned about lag in your game, what you need to do is turn off multi-threaded rendering. This will reduce the amount of throughput that you can have through the graphics hardware. It will reduce, how many polygons you can push. But what you get back is it will in effect halve the lag. I was able to bring this down to something around 30 milliseconds, 30 to 40 milliseconds, which is a huge difference. Still quite upsetting that it's not really feasible to get it down to the 20 milliseconds of the original, or at 60 FPS, 16.666 milliseconds. Of retro technology has a much lower latency. There are people who will tell you that, I've actually heard this said, right? I was complaining about one particular micro console that I supported on Kickstarter. It was the Game Stick. I never made a game for the Game Stick because when I tested it out, I found that it didn't implement VSync properly. In fact, it didn't implement VSync at all. It wasn't able to synchronize the game to the vertical blank of the display. Or the VSync, vertical sync. Vertical blank is a bit of an old term. That's from TVs, CRT TVs. But vertical sync, it wasn't able to synchronize with the video circuitry. This was terrible because it creates kind of like a jerkiness and so on. And I actually I raised this with them, and a reply that I got back, which is a very classic one, is that the idea that human beings cannot perceive anything less than a tenth of a second. Well, this is absolute nonsense. It's very simplistic to think that you can't. In fact, actually, if you've ever actually done tests and you are working on an interactive environment in some way, like you press a key and you get a response, and you go above 200 milliseconds, that 200 milliseconds can feel like a long time. Perception, human perception of the passage of time is very complex. It's not a kind of hard and fast, it's not a hardwired thing, if you follow my drift. It's not something that you can, what's the word? There is not a objective standard for the perception of the passage of time. We have objective standards for the measured passage of time, but the perceived passage of time is just something that works completely differently. The reaction time of a person who's got good reaction times can be under 200 milliseconds. But that is the whole time from seeing something to processing it to it going through all of your neural mechanisms down your arm through a nerve. It's actually amazing that it does this all so quickly, firing the muscles and then the muscles having the actual response to sort of to respond to the event. So the actual perception is much higher than the reaction time. And then there's the fact that when it comes to measuring changes in time intervals, we're very sensitive to that. And so that's where if you watch videos or even at the cinema, if you've ever noticed this kind of shuddering that you get, and generally the filmmakers try to avoid having slow panning shots because instead of doing this, well, in fact, even you can see it in my hand probably even as I do that. Look at that. As I do this, keep a lot of people tend to sort of not necessarily that observant, I found. But if you look very carefully at the sheet of paper, as I'm doing that, is the motion completely smooth? My hand, is it completely smooth? Or does it, I can see on my view here, it did actually stutter at some point. Well, those stutterings, which, I mean, I can definitely see, they're annoying. They detract from the experience. Those are timing changes which are very, very short. In fact, if you're watching something that is animating at 60 frames per second, and there is one frame within that 60 frames per second which takes twice as long, you're talking about a change from 30 to 60 milliseconds. It's a change of 30 milliseconds, and we can really perceive it. So it's actually quite wrong to say that you can't observe. We do not perceive time intervals of less than 100 milliseconds or a tenth of a second. In fact, I did, and when this happened, I did an experiment. What I did was I connected two controllers to the game, and all I did was make it so that the position of a cursor on the screen was mapped directly to the stick position. So clearly, of course, you move the stick position. There isn't a great deal of accuracy because it's a small movement for an object that moves across the screen. But there is enough control there, more than enough control there, to be able to follow a moving dot. So then what you do is you get one person to take one controller and the other person to take the other controller, and you've got a very, very simple game. It's one where one person is moving and the other person is trying to catch them up. It's like a game of tag, right? It's just simple. Two cursors on the screen, one person is chasing the other and trying to stay on top of them as they're moving around. And when you play that game with 100 milliseconds delay, it's really not fun, and it's really frustrating because that 10th of a second delay means that you're always overshooting, undershooting, and it's like... So the result of this is that video games that are made today, because our lag in games has gone up and gone up and gone up, they're actually designed to deal with the fact that not only is the lag long, but different people will have different lags depending on the behavior of their TV, of their monitors, their hardware. It's just... And then if you're doing network play, there's that lag as well. And that's one reason why Twitch gameplay is not as fun as it used to be. If you go and try to play a retro game on modern hardware, you might think that those people who want to play the original games on the original hardware are being nostalgic, but they're not. It's more than nostalgia. They actually do play differently because of the lag. Because on the historical hardware, on CRTs, with say on the Amiga games rarely were double buffered. These days, every game is double buffered. I don't know if there is actually a non-double buffered engine out there. But see, double buffering is where you display one screen while you're preparing the next. So this obviously makes sense. You're seeing this one while the next is being prepared, and then when you reach the end, you bring the one that was being prepared on. Okay, but the problem is that to prepare the one that's off screen, you had to read the input of your controllers at the beginning of that, which means that the input was read one frame before it starts to even render it. So what you've got then is double the latency, just because you're using double buffering. So when you go back to those original games, the latency was very short, in fact imperceivable. It was under 20 milliseconds, or 50th of a second. And so don't think that playing on the original hardware is just a kind of oh, well, nostalgia-y thing, is if you actually want to experience the video game as it was when it came out, you need to play it on the original hardware for very clear and hard technical reasons. This actually makes it very difficult for emulation of original games to really be effective. You can't play Defender on modern computers in emulators and have the same experience. And Defender was a game that was designed to be pushing you to the limit of your ability to process and act quickly, right? Twitch gameplay. It was, central to the idea of the game Defender. So the problem is it was never tuned for soupy delayed controls. So people today, if I like to say Defender is one of the best games ever sort of made. It's like a really great game, right? So people might try it on an emulator and they'll go, meh. But you have to play it on an actual console machine or on a CRT display. And of course, you might be wondering, well, why is it that it should be so hard? Surely you can just accelerate the graphics hardware. And there is something you can do with that. There are some things that you can do. You can render at a faster frame rate than you need. This is effectively the technique I used on Kickoff Revival. It was sort of rendering at 240 frames per second in order to try and counteract this particular problem. And to bring down the lag. It used a trick to do that, as in, although it was rendering 240 frames per second, 2 of those frames were in fact blank. It would turn everything off in the scene so it could get through them really quickly, just to push all the graphics through the pipeline really fast, right? So, but yeah, so there are some things that you can do, but in general, when you do it, what's going to happen is it's a trade-off between how many polygons you can push, and the industry has been for a very long time just trying to push as many polygons all the time under all circumstances, measuring the quality of the game by how many polygons can be pushed as being, because that's easy to measure. So that's just a trend that there's been. But if you want to reduce the latency, there's going to be a reduction in how many polygons you can push. So you have to choose, what's important. And I hope that one day the importance of latency will, be recognized again, and we'll have people optimizing game development to try and reduce the latency instead of have it forever get longer and longer, right? I worked on a video game. I won't say which one it was, and I was looking at the lag. I swear it was a quarter of a second. It was a racing game, quarter of a second lag. It's like, whoa. I have no idea if it ended up shipping like that, but you can sort of get away with it on a on a racing game, because it's all a bit like this. But even then, imagine driving a car. Everybody has this obsession with realism. I think it's changing now, but it's funny. It's a subjective realism. It's like, if you're driving, could you imagine driving a car where when you turn the steering wheel, it takes a quarter of a second before the car responds? It's like, if anybody made a car like that, they wouldn't sell it. So if you make a game that has that kind of lag in that kind of situation, then you cannot claim you're being realistic, you see. But anyway, I digress. So the whole point of this project I want to do, is to sort of have a neater way, a better way of doing the same thing. So to recap, I was recording audio that could pick up the moment when I smashed the button, that would, in the code, cause the screen to change color from black to white, causing a speaker to emit a tone, change the tone it was emitting, right? So that tone was also picked up by the microphone. So then I could look at the audio and measure the time from smashing the button to getting the response. By the way, this was before, this was a few years ago when high-speed cameras were not as prevalent as they are now. I mean, high speed, like 200 frames per second or whatever. So, the way I want to do this is, well, this is going to be interesting because what I really like is to be able to put it into a small box with a display like this that would have a microphone and you would be able to put a sensor. Either it would be on the box itself, you put it up against the screen, or on a cable, and what you would do, smash the button and it would sense a change in the display on a light sensor. It would be this, but a light sensor, measure the time interval between them and display the result as 4 digits in here. So this thing that I've got was an experiment to use a PIC. This is an 8-pin PIC IC. It's actually this guy here. That's a whole microprocessor in 8 pins. Lovely. All the rest of this here was just sort of multiplexing to be able to get this one chip to drive all these digits. And it's, yeah, absolutely fine. Now I don't need to necessarily use these, but I have a few of them. But I could use a PIC with more outputs. But that's not the point. The point is it's a little microprocessor with programmable input-output pins, microcontroller. So what I need is to have a circuit that would be able to hear a change in audio from this and detect it on a pin, and then also be able to check the change in the light falling on a light sensor. I suspect when it comes to that, I'm going to want to have an analog to digital converter, say, to convert the level to, I don't know, like 1024. A number, 10-bit number is very typical. And then, so if I had that set up, the microprocessor, which runs very fast, I think this runs at 32 megahertz, which is like 4 times faster than an Amiga. So there's plenty of power there to do the timing measurement, and it could observe when there is a change in the light after it hears a spike in audio, measure the gap between the two, and then display the result here. And this, in a little box, could probably be powered by batteries. And then whenever I want to do a test of lag, I can just do it immediately. All I need is to be able to have an input device I can hear when I press the button. Just tap it, and boom, you should get the result. So there we go. That's what I'm thinking of doing. And I was just looking at circuit. So this I got off the circuits-diy.com. And I happen to have, this uses an LM386. I bought a bunch of electronics from eBay like 5 years ago. It had like those PICs in there. I've got a huge number of PICs actually. There's like, look at this. They're all obsolete PICs. I don't know. I mean, maybe I should just sell these. This is MX230FO64B. Whoever, I've got just so many of these unused PICs. microcontrollers. But I also have an LM386. Here it is. It just so happens there was one, or some ICs. It was there. This is a circuit that uses the LM386 in order to light an LED when there is a noise. So I want to try this out. So I've got this from circuits-diy.com. So, you know, let's give it a go. I think I actually drew this out better again. Oh no, it's in here. That's right. Yeah, this is the pins. This is the pins of the IC. From pin 1, 2, 3, 4, 5, 6, 7, and 8. So I'm going to give this a go, and then maybe I'll one of the earliest electronic circuits I ever made was an LED that was lit by a microphone. That was fun. I remember going, ooh. Every time I speak, the little light comes on. It was kind of, it's like it was alive. I set my power supply to 9 volts, and I've got a nice bench power supply over here that I bought years ago. It's current limiting, of course. So I'll just put this, short out the power supply, and then set the current limits at, it's fine, it's about 90 milliamps. And I'll try and build the circuit. So what do we need? From ground to pin 4, from also pin 2 to ground, and then 4, 2, okay, and then we need to go from pin 6 to VCC, the positive power supply, and then I think the rest of it, right, so I've just also bought some pack of electrolytic capacitors and other capacitors. We need 100 nanofarad capacitor there. Where has that gone? I think another project I'd like to develop is a motorbike sound suppressor. Listen to that. It's like, wow. So annoying. Ceramic capacitor kit. I want 100 nanofarad, please. Oh wow, these are quite high values. 10 microfarad. Uh, 100 nanofarad is 0.1 is the same as 0.1 microfarad, as it happens. So there we go. So that's in this one. La 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 la. Let's get my little capacitor. Please. I'm going to try and get this out without spilling them everywhere. That's just my most common modus operandi. 104 it's got written on it, which is 100. Well, actually, 10, 5, it's 1000 picofarad. That would be. Let me just check. Oh, right. So 105 is 1 microfarad. Yeah, okay. All right. So this should be 100 nanofarad. All right. So we'll do that. That will go somewhere around here. And the other capacitor I need 2 more. A 10 microfarad capacitor, which it actually in here says use an electrolytic, but why don't I try this? Since there is one of these magic 10 microfarad ceramic capacitors. That's crazy. When I was doing this kind of stuff as a kid, you couldn't find 10 microfarad non-electrolytic capacitors like of this size. Not sure what the voltage is on these, it doesn't say. We'll see. I can always, if something goes wrong, I always try the electrolytic. So that one is the 100 nanofarad. We've got the 10 microfarad goes off pin 8. And then I need a 1K resistor. I have these are my go-to 1K resistors because they're old-fashioned. This is from that pack of stuff. Focus, camera. Focus. Maybe there's no autofocus on. Let me check. Properties. Configure video. That's the wrong one. I want this one. Properties. Configure video. Oh, jeez. No, it says autofocus is on. That's strange. Oh, it also. Oh, there we go. All right. There we go. Yeah, there we are. Those are resistors as I knew them when I was young. So that one's brown, black, red. So brown is 1, black is 0, red is 2 zeros on the top. So that's 1000 or 1000 or 1K. And gold is a tolerance band of plus or minus 5%, if I remember rightly. All the other resistors here, which are a little bit smaller, they've got an extra band, and then I have to think about what that means. So 1K resistor, and that can go from there to background to pin 1. Yeah, background to pin 1. And then what do we have next? We got the 100 nanofarad. We need a 10K resistor. I need to tidy up around here. Where are my 10K resistors? Oh, they'll be over here. I don't have any old style 10K resistors. Resistors is futile. These are 10K. This is the little 10K resistor, so I'll put that in. That goes to the positive supply line to the 100 nanofarad capacitor, which goes to pin 3. So actually, what I'll do is pin 3 is over on this side. We can put that in there. Right. So I've got that going from here to a pin blank one over there. That's the 100 nanofarad. Let's make sure I've got the right one. Right. So pop that in. Ooh. There we go. So that's in. 100 nanofarad on pin 3, no other connections to pin 3. The other side of the 100 nanofarad needs to be taken up to positive supply line by a 10K resistor, so that's this guy. Nice stuff. And what we do now, from there, so I'm trying 100 nanofarad. capacitor, 10. Right, I need to put my microphone. Now, the microphone, I have an electric condenser microphone, which also came together with all this junk I got off eBay a few years ago. Electric condenser microphones have a polarity to them. Don't spin the world. Come on, focus. There we are. The negative is the one that one of those sides is connected to the shell, so that's the negative side, and so that goes to the negative supply rail. A positive supply rail goes to the junction of the 100 nanofarad capacitor and the 10k resistor, pulling it up to the positive supply line. So I think I've done this, and this. Nearly done. 100 microfarad capacitor next. So over here I've got some, haven't opened these yet. These are good value. I think this pack was like £18. It has 630 electrolytic capacitors. I mean, they're probably not very good, but fine for prototyping. So what I need from here is a 100 microfarad. The circuit diagram off of Circuits DIY put the positive of the of this electrolytic pointing towards the chip here, and I was going, what? If the positive supply goes through this diode, the current is always going to have to flow this way, so this side should be positive. So I've reversed it here, because otherwise you're putting current through an electrolytic capacitor the wrong way round, you know, which is not a good idea. I can't really see how it could be any other way, but there we go. 100 microfarad 16 volt is this guy, and there's also 25 volts. Well, let's use 25 volt since I've got them. 100 microfarad. Let's see, let's have a look at that. Ooh, 100 microfarad, 25 volts. Isn't that's pretty, isn't it? Look at that. Oh, I'd have loved to have had one of these when I was a kid. I also got a pack of transistors. Anyway, here's my electrolytic. The electrolytic capacitors almost invariably have two different length leads on them. The short one is negative, the long one is positive. They're also indicated by usually a strip. One pin is marked differently, and it has little minuses there. So anyway, the short lead, this one, that's the negative side. So I'm going to point that at pin 5. Since the LED is connecting to the positive supply line, my argument is, you know, we need to... The only thing about that long lead versus short lead is that it always makes them a bit awkward plugging them into breadboards. All right, so there we go, that's in. And then I need a current limiting resistor for an LED. They've got 390 there, but I've got these green LEDs that are really bright and very efficient. They don't take up much current at all. So I'm going to use it's going to be pretty bright at this voltage as well. They're saying here run this at like 9 volts. If I put 390 ohms on one of my green LEDs, I'll probably blind myself. So this is my tray of components that have got scattered around, and then I need to sort of put them back again at some point. So there's my LED, which also has a short pin and a long pin, although this in this case much more reasonably lengthed than that other capacitor. It was a ridiculous difference. The short one again goes to the negative. The second way that you can tell is that it's going to be very difficult to see it, but I'll turn around like this. Yes, there we are, because it's a non-mirrored image. Hello. There we are. On that LED, all right, you can't really see it, but there is basically, you might, if you look at it this way, one side, this side's the negative side, has a flat edge. So you can usually tell with that, it's very small, especially under a magnifying glass, you can tell. Another way that you can tell is if you can see into the LED, there will be two electrodes. The bigger one is usually the negative. Anyway, I need to put that negative I'm saying negative. It's the cathode and the anode. So actually, if you want to light the LED, yes, that's only. You know what I'm going to do? It's like I'm thinking. That's a point, isn't it? Because you have to point the negative side at the positive side. And so now I've never thought about that before, and that's going. What? So what you do is you put the negative is the short one, but actually that's the anode. That's what was just confusing my poor brain. So what we do is we take that and put the negative, the short lead to the negative supply, and I'm going to take this LED, this resistor, and connect it to the positive supply. And there's the light lighting up. You can see it's blooming bright. I mean, it's practically burning a hole in the camera. Right, maybe I should use a bigger value resistor here. Where are my 10Ks? Let me try 10K. Hurry before you burn out. Before you burn out your webcam. Yeah, it's funny because I was thinking, yes, the short one goes to the negative. Then I was thinking that, yeah, never mind. Yeah. So I always tend to think of the anode as being the positive and the cathode as being the negative for some reason, probably because of valve diagrams. When I was first interested in electronics, there were actually, valves were still a thing. That's with a 10K resistor, which is still plenty bright. Okay, so what we have to do then is connect this up. Positive supply goes to there, and then the long lead, the anode, cathode, did it again. The cathode goes. Actually, let's make it go across like this, and we bend these down. So there we go, and then this is the power lead, right? And then I've got to connect the other end of this to the capacitor. Now that works. Here's the capacitor there, and now we have a circuit. And oh well, something is happening. Hello, come in, please. Well, it's very bit curious how at first it really wasn't responding too well, and now it's sort of settled down. I think obviously the problem is you get circuits off the internet, and well, they they're not always that good, or they can have problems. This particular one has an issue that although it's working quite well now, it took a little time to warm up, and that's probably because of the big electrolytic capacitor. Well, either of the capacitors. It does seem that the sensitivity is also getting lower as well, so that but I'm not sure what the output is like of this. If I'm looking at the particular chip that this is yeah, it's definitely getting less sensitive. Well, you're definitely less sensitive now, aren't you? Which could also be because there's some component is slowly dying. Some component is slowly... What's happening? I think what's happening actually is to do with gain. And the in the circuit here, the connection between 1 and 8, I've read up about this chip. This is an audio amplifier chip. This is a gain control. Now I can only assume that this big electrolytic capacitor here, well, not even big electrolytic, this capacitor here is taking a small charge, and over time its resistance is going up, and then as the resistance goes up, because it's getting more charged, we see that the sensitivity is going down. In fact, this explains why it was that at the beginning the LED was like continuously on. So I need, as expected, now we have to tweak the circuit to make it work. The other thing is I need it to work at 5-volt supply. Right now I'm running at 9. So yeah, look at that. It's hello. So let me see if we can, well, we'll experiment. The first thing is that this connection between pin 1 and pin 8 can actually be removed. If you do that, then the gain drops. It's not entirely clear from the person who designed this circuit why they threw that electrolytic in there, although in looking at the spec of this thing, putting in a capacitor in here is, you know, one of the operation modes. It wasn't clear to me why a capacitor as opposed to just a resistor. As you can see, it's still working, but the gain has gone down. The gain has gone down because presumably the resistance has gone up. Let me just try this 1K resistor only without the capacitor and see what happens. Hello, 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 hello. Yeah, it did increase the gain. So but I don't want to put a short on that. I don't want to go too low on the resistance I use in there in case it causes some kind of damage. So it's also possible that there is a reason why an electrolytic was being used. It could be that electrolytics are a bit leaky, I don't know. And that was being... So let me just try their circuit. I need a 10 microfarad electrolytic here. 10 microfarad electrolytic. Doobie doobie doo. If I hit the microphone, it lights up. So although this is an audio amplifier, you usually use it to sort of generate, you know, like for a small little speaker in a device. You can also use it for other things, apparently. So from pin, I'll check the polarity of this electrolytic. It makes sense the way that it was in the diagram. So I'm putting in the electrolytic there and my 1K resistor with the negative on the resistor, and then we go from, come on, get that in from there, and we go to here, And what do we have? Hello? Hello, how are you? Are you alright? What's going on? Hello? Yes, not very sensitive. Might be sensitive enough for my applications. But that's kind of interesting that the electrolytic is behaving differently to the ceramic capacitor by the looks of it. No, it's about the same. So maybe what I'm going to do is disconnect the power and let the thing discharge. Maybe dooby dooby doo doo dooby doo 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 doo. Just use a 1K resistor to discharge the two capacitors here. Probably use a lower value, but whatever. Right. I want to understand why it changed. So first of all, I turn it on, and you can see that the LED is on all the time. I don't know whether it's picking up noise, as in electrical noise, or actually audio noise, which is making it do that. But now it's settling down. Which capacitor is causing that? It could be the one to the LED. Actually. Oh. Yeah, oh right. Okay. It's the one to the LED. So what's happening? Yeah, this circuit is a bit weird because what's happening is that the LED is in effect acting like a rectifier, and it's charging this capacitor. So as the thing gets used more and more, it charges the capacitor more and more until eventually the capacitor's effective resistance increases to the point that there isn't enough voltage over the diode to light it, or it's harder for it to light it. So I think this shows a little bit of a mistake in the person who designed this circuit, because there's no opportunity for this capacitor to discharge itself. So I think the fix for this is to add a resistor in. When this connects to ground, when this gets pulled down, the more it gets pulled down, the more current flows in through here. But presumably this is just an amplifier, so this is an AC signal. The purpose of the capacitor is to sort of remove the AC component. It kind of really doesn't even need the capacitor. I don't think it even needs the capacitor. We'll try it without the capacitor. Hello? Ah, right. No, it needs the capacitor. Yes, because otherwise this voltage here is always offset as a bias. So what the capacitor is doing is removing any DC bias. So what you're left with is an AC signal, which is generated from the variation of a DC signal. Well, it's an AC is superimposed upon a DC, so it's a wave like this, but at a higher voltage level. So that what the capacitor is doing is decoupling the DC, if that's the right way of putting it. But it actually has no discharge path. So I think the right thing to do is to try putting a resistor between the negative side of that capacitor and the positive supply line, and then it has a discharge path. So I'm going to try that. So from there to there, and then we'll get a little cable and try to put that in. So positive supply via the resistor, and then so yeah, so the resistor goes on to pin 5. The LED needs to connect to the other side of the capacitor. 1, 2, and now it seems right. The test is going to be to discharge. So I'm just going to disconnect the supply. I'm just going to use my screwdriver to discharge that electrolytic capacitor, and we'll see if it's better behaved now. Oh, and it isn't. Well, I suppose the issue is that the capacitor is so big it takes a little bit of time for it to settle down. But at a certain point it should be more stable. So there's kind of now a warm-up time. But the question is, does this continue to become less sensitive over time or not? And if this trick worked, then it should be more stable. But you know what? I think also that capacitor is a bit exaggerated. It's like put a 100 microfarad capacitor in there. I don't think it needs to be that big. Although it's interesting because it is directly driving an LED. It is directly driving an LED from a from a power amplifier, though. That's the whole point. This is a power amplifier. It should have the current to drive the LED. I think that we can get away with a smaller capacitor as well. 1, 2, testing. Right. Let's try other values on that capacitor. So if I take this out, and now I'm going to replace it with this 10 microfarad capacitor, and that will go see that you can see it warm up as well on that one, but the warm-up time is much less. Let's try that again. Go to short, like a bucket of water. It takes less time for it to reach the balanced level between water going out of the bucket and water going in. Hello, testing. 1, 2. How are you? Hello, is this stable? Are we strong and stable? 1, 2. 1, 2, 1, 2. Yeah, its sensitivity is going down again. So maybe that was in the experiments that were done on this by the circuit designer. They decided this was a good capacitor to use. 100 microfarad. But see, it has a problem. I mean, right at the beginning, it's just like on continuously. And actually, it makes sense because even in silence, there's going to be a voltage on the output of this. And so this is equalizing. And so as it equalizes initially, there's a draw of current through the LED. So what I suspect might be a better thing to try here is to use a different circuit design to this, where it's not trying to do the detection or the rectification of the audio signal and the display of the audio signal with the same component, which is the LED. Ultimately, this is... Oh, well. Let's have a... This is where an oscilloscope comes in useful. We can analyze it and see what's going on. So I've got this recently, very nice. Turn it on. I'll be back shortly. I just need to get a drink and stuff. So I'll be right back. Okay, so hello, how's this little LED doing? Still kind of working. Let's connect up a scope probe. Always keep your workspace tidy. Is not something I actually adhere to in practice. So we can plug that in there. And I should be able to get, let's just make sure that this thing is, I'll hit the auto scale button and we should get a nice view of mains hum. There we go. There's nice view of mains hum. Yes. If you ever need a signal, a low frequency signal, test signal, you can always just use your finger. As your finger is the generator of 50 Hertz in the UK. In America, fingers generate 60 Hertz. It's picking up just the electricity supply. It kind of makes you think. It's a good thing that it doesn't do anything to us. But who knows? It's not exactly natural, is it? A 60 or 50 hertz continuous electromagnetic field around us all the time. It's just one of those weird things. There's actual scientific evidence that our bodies do respond to electromagnetic waves in subtle ways. So it's like, who knows? We don't really know. At some point, somebody goes and discovers something new, completely changing the viewpoint on something or other. It happens all the time in science. So anyway, I've got this connected to the negative side. Asking the question, by the way, isn't the same thing as being a crackpot. I don't think there's any problem. But you never know. You never know. You never know. Just that's science. You never really know. Not really. Otherwise, science would be done. Science is never done. What I'm going to do is examine the output of the capacitor here that goes into, well, in fact, through the LED. So I put that in there messily, but whatever. Are we still? It's still working, but actually, it seems to be less sensitive when I put the lead on there. Is it? No, it's my imagination. It's just that capacitor keeps charging. I'm disappointed that my no, I know what's wrong. What I did was pretty naive. I put a resistor across here so the capacitor could discharge, but all that's doing is it doesn't really change anything. If I had a diode there, that might help. The discharge... No, maybe not. Yeah, it doesn't. It's not really gonna. It's not really gonna help the fundamental problem. All right. So anyway, I'm going to take that resistor off then. Let's short out the capacitor. Hello, testing. 1, 2. Right. I'm going to put this on there. And just hit auto scale and see, oh, while I'm talking, what kind of signal are we getting? Not a lot. Oh, no, wait a minute. There is my voice. You can see my voice. So that's pretty good. And I have the input. Let me turn off the measurement display. There we go. Yeah, so as I'm talking, I've got my voice appearing on the old oscilloscope-a-rooney. If I turn off DC coupling, it's on DC coupling right now, sorry. If I turn off DC coupling, I'll go to AC coupling, and then it hit auto scale while talking. It is important to keep talking for the auto scale to scale to thing automatically for my voice. So it doesn't seem to have worked. Oh, hang on. There it is. And then I can sort of get the position. Well, that's curious. I should be decoupling. Oh, right. It always switches it to DC when I do auto scale. That's really annoying. Can I have an auto scale with it being AC? No. Let's turn that on. Right. AC coupling. And then I'll have to manually set, but where is it? There. Why did it disappear? Wow. I'm not sure. That was this oscilloscope is a bit buggy. So right, what I have is the center line is 0 volts on there, and now it's measuring my voice, but it's in AC coupled, which means that it's removed any DC offset of the signal coming in. And what I wanted to do is just short out the capacitor and then observe what happens. So we do this, short out the capacitor, and while the capacitor is charging, and you notice the LED is staying on because initially there's more current flowing through the capacitor, but it doesn't seem to affect the operation of the AC signal component, which means that basically I need a better detection of the audio signal than this very crude circuit, which has this issue. I think as I'm talking, it doesn't seem to be reducing the sensitivity at all, even though the LED goes off. Now, what I can do is put it back into DC coupled mode. Now, of course, I can't see the display because it's gone way off. I need to sort of bring this down. Right here, is that it? Oh, there we go. And I can actually see that the there is a voltage offset, and I want to really track that. So what I'm going to do is reduce the sensitivity, the vertical sensitivity of this thing. Hello, where are we? There we are. Oh, this scope is quite nice. It's very good value for money, but it is buggy. The software on it is a little buggy, but not to the point of making it unusable. It's just more annoying. So you can see the voice signal is still there, but it's sort of added to a DC signal. And I'm going to short out this capacitor again. And I don't know if you can see there. Let's just increase the... I short out the capacitor. Hello? 1, 2... oh. Circuit catastrophe. Shorting out the capacitor should be fine. It doesn't not going to cause any circuit issues, but things fell apart. Hello, testing. There we are. So it's working. I need to put that on there. So if I short out the capacitor, as I have done, can you see that line is moving upwards? So the voltage on this, the anode of the LED, is gradually increasing, because as the capacitor is conducting more, it's pulling the voltage down to ground. Then as the capacitor becomes more and more charged, its effective resistance goes up, and so the voltage at this point is going up, because I'm measuring the voltage on this side of the LED with a resistor to the VCC. If I measured the voltage across the LED itself, it would be constant when the LED is conducting, because that's one of the side effects of an LED, is it acts like a little Zener diode, and at a voltage of I think 2 volts for LEDs, around 2 volts. It's all very interesting stuff. But anyway, so now the interesting thing is I'm looking at that and I'm saying, well, the voltage change isn't that great. In fact, the LED needs 2 volts across it for it to actually turn on. So I suppose what's happening is this, it's just hitting that sort of threshold. That's funny now, it's actually staying on a lot more than it was before. You might be picking up low frequency sounds. Hello? Testing. Yeah, it's not very stable. I want something a bit more stable, so I'm going to think about how this can work. So I think a better way of doing this would be to use a kind of rectifier circuit with a smoothing capacitor. A bit like a power supply. Where is my pen? What a good question. I don't know. Where is my pen? Now, logically, it should be still around here somewhere. Where is the pen? I have a dependency. Right, well, nothing for it. I'll have to find a different pen. Well, that's strange. We can use a pencil instead. I've lost my qualifications for using a pen, so I'll have to use a pencil. So what I can do instead of this circuit is take the output of that and then put it through a diode. And then to an electrolytic capacitor, a smoothing capacitor, which goes down to ground with a load. I suspect I will need to put a resistor like this, then also a resistor like this, and a diode like that. Now my reasoning for this circuit, this load, and this is part of maybe what's going on here. In fact, actually, I was just thinking I could put a resistor across this diode. No, well, let's try. I'm going to try this anyway. Yeah. So the reason why I was thinking of putting, well, I don't know about this, but this resistor here, is that for this circuit to work, if we remove the LED and we just had a voltage that goes up and down depending on the level of my voice, I should be able to see it on the scope. The scope has a very high impedance impedance input, because you don't want your oscilloscope to modify your circuit much. So in that case, if I didn't have a load on here, I don't have something that's sort of like drawing current away from this setup, then we have the same problem that we have here, which is that the capacitor eventually just gets full, and you know, you don't get much of a variation of stuff going on, right? I mean, once it's full, it basically will smooth out all of the signal and it will be lost, more or less. It feels like what you need to do is have a resistor across here so that you're drawing load from this circuit, and so when the signal isn't present, the capacitor can discharge and the voltage across here can fall. What's interesting of putting a diode here as the load is that it needs to be remembered that you need at least 2 volts across here to light this. So then the behavior is different, because this is having the sensor, which is the LED, is having actually a direct effect upon the sensing, which is what's happening here. If we were to remove the LED from the circuit, the behavior of the voltage here would change. So what may be even better would be to put an LED driver in here, so that we have a high impedance input, reduce the amount that the LED affects the circuit. Now what my intention is with this is to actually feed this output to a high impedance input, because there's going to be something sensing this. It might be an analog to digital converter. It could just be a digital input, which is flipped by the audio signal. So this is the LED is a cheap and cheerful indicator, but it's not actually useful for what I want. So what I'm going to do is study the behavior of the circuit with the oscilloscope and not use the LED, because the LED is influencing the circuit. And so then what I need is diode, capacitor, and a load resistor. So I'm going to try that. Just take this off, and then I'm going to remove the LED and its resistor. And we also remove this capacitor. So that capacitor will come back in a minute. So what I've got now is just the output of pin 5, which I'm going to feed through a diode and to charge electrolytic capacitor with a load. Then I wonder, if I should put a resistor in front of the electrolytic. Oh, we'll see. Right, well, diode. I do have diodes in this pack, that electronic pack from eBay. There's a whole bunch of fairly typical signal diodes. I will test it to make sure that this is actually what you think it is, which is a silicon diode. So this type of circuit, which is I believe called a detector circuit, is used in the earliest radios. What you do is AM radio, you have a radio signal that is modulated as it gets louder and quieter very fast according to the voice. You need to get rid of the radio frequency and leave the audio frequency, and to do that use a detector circuit, which is basically a diode to rectify the signal, and then maybe you have a little bit of capacitance in there as well. And what you end up with is what's the old crystal sets, the way they would work. I actually built one a long time ago as a school project, and it actually worked. It was a coil of wire and a capacitor, tuning capacitor, and a diode and a crystal earpiece. I think I even have a crystal earpiece, came in this junk somewhere. A crystal earpiece, which is like a very, very efficient, not very loud, sort of like headphone, very high impedance. And if you connected this to a long wire, there's basically enough power picked up by the wire to go through the capacitor and inductor coil that act as a tuning circuit, go through the diode and into the earpiece, and you have a radio that doesn't need any batteries. And it worked. It was pretty cool. So this diode is going to be my detector in here. And I take the output of pin 5. I'm going to pop it in there. And then I need to take my electrolytic capacitor. This is the 100 microfarad one. This is going to smooth the a result of the detected signal. So that side, which I've got the negative side going to ground, so that goes to ground. And then we could just try this actually as is without a load and see what happens. So if I put this on here, hello, testing. Now I don't know if you saw, the behavior is completely different now. You can't see any audio signal, but when I said hello loud, this thing moved up, didn't it? So it's like beginning to behave a bit like a VU meter, but with the capacitor value that I have right now, it's a very sort of slow one. Hello! Look at that, is that great? Because I don't have a load capacitor, a load resistor. So what's the capacitor is discharging essentially through its own internal leakage. And so that's why that line is coming down really slowly. So what we'll do is add a resistor and put it across the capacitor. So this is now the load resistor from there to there. So let's try. I can actually do it like this. Well, keep life simple. The diode is feeding the capacitor, which goes, but also the resistor, and I'll connect the resistor to ground here. So we just do this. Now what I expect to see, this is actually now a noise meter. Hello. Now it's not easy to see what's happening too much because the frequencies that are being picked up here are quite low, because the high frequencies have been filtered out. So what I'm going to do is change the time base to work at a lower frequency. Now, when you're doing this kind of stuff, it's nowhere near as nice as an analog scope. They're just so much more immediately responsive. It'll be kind of interesting project to develop a digital scope that emulates an analog scope and actually behaves like an analog scope. You can see update. There is a mode that you can put this in that might be better in this case, which was trigger menu. I can't remember now. Zoom 0. I know I saw it somewhere. Oh, wait a minute, it's display. No. Utility. No. Oh, I know I saw it somewhere. Now I can't remember how to get to it. Cursors, measure. I'm sure it was the display button. There are two screens. Persist off. No. Screen brightness, source, display type. Acquire. Acquire mode. No. Display mode. Roll. That was it. Okay, so in the roll mode, which oscilloscopes, it's better to use these digital oscilloscopes in this mode, because you can see the wave moves past like this instead of it sort of updating it over time. She gets too hungry for dinner at 8. She loves the theatre, but she never comes late. Yeah, alright, so I need to tune this to make it a little more sort of interesting. We're looking at this in a DC sort of realm. If I hit measure here, I can see what the 3.6 volts, I think. Hello. Yeah, I want to improve the sensitivity of this, I think. If I get rid of the load resistor. Hello. La la. It's gone all the way up, and then it's... So a number of things I can tune here. I think let's use a bigger value, a higher resistance for the load resistor. I'm going to try 10k. She gets too hungry for dinner at 8. She loves the theatre, but she never comes late. She'll never bother with anyone she'd hate. That's why the lady. Alright, 1, 2. See, that settles down. Sort of, it settled down not too badly, actually. That seems to be pretty good. Now, I want to know what the voltage range is here, because it says 2 volts. Is that 2 volts per... I suppose it's 2 volts per... Let me hit auto scale and just... Didn't do the auto scale. I think it's 6 volts. I would say think because I'm not entirely clear and sort of trustworthy. Yeah, actually I see there. It's about 6 volts. That's correct. Yes. It's 2 volts per centimeter. So we're on 6 volts, measuring the output of the capacitor, the smoothing capacitor. La 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 la. Utility, acquire, display mode, roll. La 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 la. Alright, so that's fine. I've got some kind of visual indication here. The variation on input voltage, we're about at 5 volts at the moment. I want to know why I saw 6 volts before. 6? Well, I don't know. La 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 la. The variation I've got is around about 1 volt. What I really want to do is to have this with some kind of threshold, right? So the first step is I've smoothed the thing out. But I need to, to get a robust detection, audio detection circuit in here, I need to have a threshold. Of course, I could put a decoupling capacitor. I could remove, well, let me just try removing the DC component, because I'll do that by putting a capacitor in series after this, so that you know, the offset is, and that would have to do that because you're not really interested in the precise DC level. You're interested in the AC signal level. If I go and there we are, switch this to AC coupling. So now, la 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 la. The problem is that the signal is so slow moving that the AC coupling has filtered it out. So I could have a further amplification stage, but I mean, really, it's going to be overkill. Okay, let's put it back onto the DC coupling. Hello? Right. And let me just also check something else, because I wanted to have this at 5 volts. So I'm lowering the supply voltage. So now we're on a supply voltage of 5 volts. Hello? La? And the thing has died. Oh. Oh, right. No, it didn't die. What actually happened was that I reduced the voltage of the live circuit. The capacitor was charged higher than the voltage in the circuit, so it had to settle. So let's... I've just disconnected the supply. To reconnect the supply. We're still at 2 volts. I'm going to increase the sensitivity. We're at 1 volt per segment, per cell, whatever. This is around 2.5 volts. Did you hear that? 2.5 volts. Okay. Right. What would happen if I reduced the value of this resistor here, which should affect the gain of the amplifier circuit? So I've now got 2 1K resistors in parallel, which gives us 500 ohms across pins 1. Hey! Hi there, Zag. Welcome. First person on this stream. This is an electronics stream. I've been wanting to do one of these for a while. So just to fill you in on what's going on, I'm making an audio detection circuit in order for a potential project to the future. You might remember a while back I did this thing. It was an experiment to run 8 7-segment displays. I should say 8, because there's also the point. 8 LED display, whatever, off of one 8-pin PIC. And so this was, I programmed this to sort of run count through this in hex, right? Well, what the idea is to create a thing that has one of these. So it's a 4-digit display driven by a microcontroller that has 2 input interfaces. One of them is an audio interface, which is what I'm experimenting with the electronics of the audio interface right now, which is quite interesting, using my new oscilloscope that I got. Finally, the first time in my life, I have a proper oscilloscope. Long overdue. The other input would be a light sensor. And so the project is to measure the time interval between a noise and a change in a light level. What's the point of this? You could then use it to measure the lag in video games. So for example, you have a video game and you want to know what the lag is for you on that video game on the controller to whatever. What you do is you take this device, you point it at a portion of the screen that can modify when you hit a button, you prime it, and then you tap the button. Now maybe the sensor will be on a little lead for convenience, and you can just sort of stick it with a bit of blue tack to your screen, right? But once you've done that, you prime it, and then it's listening for a noise. And when you smash the button, it can hear that you hit the button, so it gets the time that the button was pressed. And then it detects a change in light level. When it sees the light level change, it knows there was a response from the game for the button that you pressed. Measure that time interval, display it on the display. I would love to have this device, because then whenever I want to know what the lag is in something, I can actually measure it. So there we go. There's the project. So right now, I've just been using a circuit that I got off circuits.diy.com that used an LM386 audio amplifier to detect audio, and that was working, but it was not a great circuit. So now I'm kind of enhancing it, and this particular version of it, what it's doing is it's detecting the noise from this electric condenser microphone, and then the output is going through a diode. Excellent, but you don't have enough of 9 digits to measure lag in FIFA 21. I can never do enough, can I? But it doesn't lag in FIFA, doesn't matter. Come on, let's be honest. I mean, the game is decided at the kickoff. In FIFA, I'm sure, in FIFA, no, I have absolutely no evidence of this, but it would not surprise me, which is an opinion and not a statement of fact. And if I was actually wrong, I'd just say, hey, I was wrong. I'm not going to try and make any claims. I don't know anything about the workings of the internal FIFA. I can only tell you how it feels, how those games feel, and it was Pro Evolution Soccer had a similar kind of thing. My fear, let me put it this way, is what I fear goes on under the hood in FIFA is that the moment that the kickoff has happened, it has already decided the result of the match. And then you sit there and you play with the thing and so on, but at some point you have to shoot. Do you score? Do you miss? It just rolls it looks at the table and says, well, in the end, don't forget that in this match, they have to win, and it just fixes it all. So the point is, I have no evidence that that's the case. I just fear that it is the case. And if the point is that if you have gameplay like that, it's brilliant for dealing with lag, because it doesn't matter how long the lag is. You might as well turn it into play by mail. Oh dear, I'm terrible. Rant. No, good one, Zach. So this detection circuit, it's a rectifier that charges as it gets filtered by an electrolytic capacitor with a load on it, and as you can see, as I'm speaking, it goes up, and when I stop speaking, it goes down. So I could use this to drive a microcontroller, but the question is, how do I handle sensitivity? What about the response time? You see, this is important, because when an audio signal arrives, it's going to charge this capacitor up. It has to charge that capacitor up. And so it can take time to charge the capacitor, and so then there will be a delay. But fortunately, I've got an oscilloscope, so I can actually measure what the delay is. So I think what I want to have now is a circuit that is digital in on or off. depending on whether there is noise of a sufficient level around. It might be that it would need an automatic gain control. I don't know. I hope not. Right now, this is 1 volt per scale thing, whatever. The variation I'm getting is around about 1 volt. It's running off a 5 volt supply. So I'm just thinking about the best way to detect this. If I go and put a decoupling capacitor in there, it's not going to really work too well. Because it's a low frequency signal. It's sort of all, you know what it feels like is that I should have a circuit that is averaging this and then doing a comparison. Oh. Well, that would be fun. Can I charge two? I don't know. Yes, I could. I mean, sorry, I've got ideas going through my head here. But what we have here is something detecting noise levels. Of course, if you're in a noisy environment, like that, you're going to have a kind of increase in this thing. The other side of the issue is that I need to have a reference point to be able to understand whether the noise level is going up or going down. So one of my favorite algorithms for doing this in code is to use moving averages. But in fact, I have a moving average here. I mean, this sort of rectifier and capacitor circuit is like a moving average. It's averaging out my voice. So why don't I have two moving averages and compare them? The circuit here would become a little more complicated. I would need to have an operational amplifier. I think I do have one quad operational amplifier chip. We could try that. So in theory then, if I feed into the operational amplifier the two different smoothing averages which work over two different times, then this is a great way of detecting a change. You've got a baseline, which is the longer time average, and then to detect a change from that you use a shorter average. I could feed one into the positive input of a operational amplifier, another into the negative input of an operational amplifier. The output I would get, it would be effectively something that jumps to either completely positive or completely negative. I would get a square wave out of it, depending, flipped either to positive or negative, or square wave, it would be a square shaped thing. With the timing is, or the whether it's high or low, depends on which of the averages is higher, if that makes sense. So let me see if I can. Well, this is a 4-channel oscilloscope, so it would be quite interesting. Oh, not only is it a 4-channel oscilloscope, it's also got a maths function where you can make a trace, say the difference between two. So I think what I'm going to try is take this capacitor, which is a 10 microfarad capacitor, and use that as well. Now, the problem is on this circuit that if I try and put the detection of another detector, another filter on this side of the diode, then all I'm doing is putting the two filters together, and it will just like one filter which has a different sort of timing. So actually what I'm going to do is put two diodes here. So there are two completely different detector circuits which work on a different time domain. For this I need another diode. Now, but seriously, on the topic of football games, I always had a problem with Pro Evolution Soccer because it felt like there was this doors were either open or closed. I started to get a sense of what the algorithm was. Because I was playing the game at Precision in Italy, because they would play Pro Evolution Soccer at lunchtime. So I would play the game. And I was going, I'm trying to shoot, I'm not getting anywhere. I don't seem to be able to score. But sometimes I get the sense that this time it's going to work. And I was beginning to make a connection between the offside trap and the probability of scoring. So if you did a move that broke that successfully got through the offside trap, it felt like the chance of you scoring would increase. And you could see how you could make a game that way. Yeah. Oh, I broke the offside trap and I shoot and I score and yay! But it's sort of a bit phony if it's done that way. It just felt like that was done that way. I'm not saying it was, but it felt like it. La porta chiusa. The door is shut. And you get the sense, adesso la porta è aperto. It's like the game has opened the door, and so now there's this window that you sense is where you need to get down to the end and shoot. And really, where you shoot doesn't matter. Is if you get a shot, you will score. That is it's fine. People find that fun. That's all right. But it's like, can we also have gameplay? There's also room for gameplay that's not phony, if that was in fact phony. Might not have been, but it felt like it was. You could see it. You'd be there all lunchtime. I haven't scored. I haven't scored. I haven't scored. And it's like you watch your opponent. They break through the offside trap, immediately score. There is more evidence of that. That, for example, you would shoot at the goal, and what happened was like from a list of possibilities, and one of them was that the shot would just bounce off the top of the netting. Now, the probability of making a shot that bounces off the netting, the top of the netting, right above the bar, is actually very low. It doesn't happen very often because, you know, essentially the shots are random beyond a certain level of accuracy, and it's not that likely that it just happens to go and just land on the top of the net and bounce off. But you would see this happen at least once a game, maybe even more than once a game. And so that tells you that the trajectories of the ball are pre-calculated. They're calculated before, you know, when they are kicked, and don't have any connection at all necessarily with what you are doing with a controller. So there was the one of the guys at Precision who played PES a lot. I said to him one day, look, show me something. You're taking a free kick, right? Shoot the ball to the right. And say, went and did it. They said, yeah, look, see? Okay, do it again. Yeah, see? I said, do it again. And this time it went to the left. And he was going, what? It's amazing how far you can get with smoke and mirrors. If you win by one goal, you would have no chance not conceding a goal in the late game in superstar level. Yes. A guy posted 5 pages explaining how the AI was rigged in human versus CPU matches. I stopped playing after having a read because it was so true. Yeah, okay. So I'm not the only one who's noticed. And the problem, ultimately, if anybody makes games in this way, the problem is that they're substituting the craft, the art, the work of game development. They're removing that and replacing it with pure engineering. It's like, if you have a lookup table, it's easy to do. Have a lookup table. Don't try to make it that when you kick the ball, the goalkeeper has to try and save it. Kick the ball into the keeper's hands. Oh, that's not what I'm about. I would never make a game that way. It's just horrific. It's like, that's totally against the whole philosophy of kickoff. It's like, let the player kick the ball, let the AI figure out how to save it. Then you have something that's meaningful. But it got so bad that even when I had once made a game, one of the potential suitors for Soccer 2, one of the potential publishers for Soccer 2, rejected Soccer 2 because they said that it couldn't be done. This was in the early 2000s. Said it couldn't be done. When we had made a demo showing it working. It's just like, what? I would use an algorithm that basically, and this is the same one that was used in Kickoff Revival, by the way, is same idea, is that there is a method of finding out where the position of the ball will be in the future, and the AI of the goalkeeper is solving a rather complex solving thing, but no more complex than any other complex thing, really. It just involves some mathematics. So, you know, the state of mathematics these days, an understanding of mathematics, it kind of elevates it into the realms of it can't be done, you know. But using mathematics to solve the problem of how to intercept the ball with a set of animations available to it. I've done it several times. I've done it at least 4 times. But there you go. So if anybody is interested in how you do this, or thinks that it's impossible, they can always talk to me, where I can actually show them that, you know what, it is not only is it possible, but I've done it 4 flipping times. It's crazy. You know, it's like, and it's symptomatic of a bigger issue, which is just that the state of video game programming as an engineering discipline. Those 2 words, engineering discipline, is treated as neither a discipline. I feel it's a tendency in the industry to treat it neither as a discipline and neither as engineering. It's just get it to work. You know, shortest route to something that seems like a good idea. Where is the pride in what we do? Where is the thirst for understanding the wonderful mathematics that underlies our models of reality? And if you're not using mathematics in making video games, well, a video game is a mathematical model of reality. So there's something wrong. You know, there's something wrong there. And it's like one of those things that one of my motivations for you know, making Kickoff Revival was to prove it can be done. But sometimes it just feels like people are not interested. Yeah, there are so many things we can do. It's like, oh no. Yeah. But anyway, what has happened here? Right, I was creating a second. I was ranting. The problem is, I realised if I'm doing electronics and I'm ranting, it means that electronic components get scattered about. I've lost my capacitor. I had a capacitor in my hand, and I probably just went like this, and it flew off, and joined. It's gone to the place where these things go, I suppose. No, it went in the breadboard. Okay, it isn't as bad as all that. That's fine. Alright, okay. Right. So this. What was that? I have what was the value of that? Oh yeah, it's a 10k. I put a 10k resistor in there, didn't I? So yeah. Is that really 10k? It depends which way you read it. There's these new, the more modern colour bands on resistors can be ambiguous. I mean, this one is brown, black, black, red, brown. So is that brown, black, black, red, brown, or brown, red, black, black, brown? Anyway, they're both. It's brown, black, black, red, brown. 10k. So I have another 10k resistor. I think this is because I'd already got this one out. Okay, so get this the right way round because I put the electrolytic capacitor the wrong way round. Oh no! So I've created two detector circuits now, consisting of a diode and electrolytic capacitor, one of which might be damaged now, I don't know, and a resistor. So if I check the output of this one, this is the bigger, this is with a 100 microfarad capacitor. Okay, and then we can go from there. We can try it with a 10 microfarad capacitor. It's taking a while to charge. Hello? This is very confusing. Yeah, that was a bit confusing. So, oh, no, I had it the wrong, I was dealing with this in the wrong way. So let's just, right. So I need to go to the negative. Like so. And then I need to put the 10k resistor across the electrolytic. I have the wrong configuration there. So the 10k is a load resistor across the capacitor to discharge it. So what I should do is actually put this lead on this, and I can just poke that in. Right. So this should be, it's not working. What's wrong? We seem to have a problem with this device. A little unclear what happened. It's just the circuit is dead. We have a problem. It no longer works. Right, well then let's remove the second detector and backtrack. No! Is the power on? Well, that's a bit troubling. broken something. Right, simplify some more. Take that out. That goes in there, blah blah blah. Pin 5. Let's check the voltage here. Well, we can see that's very nice actual. That's showing the waveform from the voice very nicely as going up and down around 2.5 volts, which is it's oscillating around half the supply line, which is quite nice. But my detector circuit is not working. In actual fact, I was thinking about this. You could argue that if there's always 2.5 volts across the diode, then why do I need the diode? Because it's never going negative. That's a fair question. I was thinking, bad thinking there. Right here, so I don't need the diode, it's always going to be forward conducting. I would need the diode to detect a DC. Actually, yeah, and well, that would have made sense before I had the idea of comparing two time. The two moving averages. If I connect this directly, what's going to happen? I could try. Is it likely to blow anything up? No, probably not. Hello? Let's connect this up to there. Hello? Testing. 1, 2, no, that did not work. It did not like that. Hello? Oh, that's dead again. Completely dead. Maybe I blew up the chip. Hello? This is not good. I think I blew the chip up. I said, will that be alright? Oh, I'm sure it'll be fine. Because I've only got one of these. Hello? Hello? There's something going through, but it's not behaving anywhere near like how it was behaving before. What have I done wrong? What? Oh, it's a bad connection. That's often the problem with these breadboards, is that sometimes you get bad connections. Right, that's working now. Okay, so I can feed this output into the filter. Hello? And this doesn't work. And then it stopped working again. Let's try it like this. So the circuit is working, and then I go and connect this to there, and oh, right, if I do that, hello, seems to want the diode. yeah. Yeah, okay. Because when the voltage comes down, then the capacitor is trying to send a current back. So I think you do need the diode. Let's put the diode in. Hello? There's... Hello? Okay, right. So, there we are. It's now working again with that capacitor. I'm going to just try to swap out that one and put this one in instead. Hello? Ah, right. Now we're getting somewhere. You can see that on this one, the fade is that, you know, the spikes are a lot shorter than if I put in, which you'd expect to be the case, than if I put in a 100 microfarad capacitor. 100 microfarad capacitor. Okay, so now I want to have both. So let me try reconstructing the two circuits again. Actually, I'll put the other filter this side of the chip, then it is actually going to be, there's more space. So the second filter on here with this going down to there, and then I connect that to the negative supply. I need my 10k load resistor, across the electrolytic capacitor. That's it. Now if I take my probe and I put it on the second detector circuit, alright, those are short peaks over here. Takes longer for it to come down. So with the two detector circuits, I want to compare them. So I'm going to connect up a second probe. This one is going to connect to the short filter as opposed to the long filter. Let's turn on both. There we have two traces. Hello? That's fine. We're going to increase the... Oh, come on. Increase the sensitivity of that's actually, they're both on top of each other. Oh, look at that. That's great. And now you can see how it should work. Although I can already see that there's a bit of an issue. Because it's not really like a moving average. It has a very... It has a... Let me just get a... I could probably stop it. Where's the microphone? Okay. Yeah. So on there, you can see the yellow is the scope trace for the slow average, the blue one for the fast, and so the tail is quite different, but what we can see there is the attack is the same, and so it's not really an average, it's like a peak meter, like a peak VU meter or whatever. And that's not what I want. I need it to rise slowly, not instantaneously, in order to be able to detect that something has gone above. This is going to be poor results. So the way to do that is to insert a resistor after the diode, so that, because right now when the diode is forward conducting, it charges the capacitors very quickly, and then when it isn't, the capacitors discharge at a different rate, and that's what we see here. So tell you what, I need, what do I need? A couple of resistors. We could try 1K resistors. Some in my loose components box here. So this is a 1K resistor. I will need 2 of them. I mean, I could try like using one that's shared, but then that means they interact with each other. So I'm going to put these after the diode. So one in there, and we're going to get another 1K resistor. There it is. No, that's 1.2K resistor. At a certain point, it's not worth the chase anymore. 5, 4, 3, 2, 1. We'll get another one out of the fresh one. There we go. So there's a 1K resistor, which we're going to use for feeding into also the long filter. So this should change the behavior so that instead of peaking together, there should be both a rise and fall time. There should be a rise and a fall that will vary between the two. Let's give this a go. I'm going to start running this again, and aha! I do like it when a plan comes together. La ho ha he. So what I'm going to do is a clap. I'll make a nice clap here, and then I'll stop it, and you can see what's going on. Now, one thing you'll notice is that the amplitude of the peaks is reduced, and that's because the feeding of the capacitor is now through a resistor, and so that is limiting the output voltage that we're getting. So it's actually squashed the thing somewhat. But what I will do is increase the amplitude of this scale so that it's half a volt per thing, and then I'm going to make it so the bottom of the trace is 0 volts. Line them up like that, and you can see the blue one, and there's the yellow. Maybe I can expand the horizontal trace as well. Let's And the blue one is the filter with the smaller electrolytic capacitor. So it rises more quickly than the yellow one, which has the non-electrolytic, well, that has the bigger electrolytic capacitor. And so the detection circuit here is going to be interested in the difference between these two. If the blue one rises above the yellow one's about there, and there's the blue one, boom, then you can see it if I reposition this like that. Basically, that point is where there's a potential detection. This now becomes a fairly sensitive detection method that would be detecting also a little peak here. So clearly there needs to be also a threshold between the two, and if you exceed that threshold, then you say there is a noise, and then it would flip the circuit. I quite like this method. We can, and I think it's responding fairly quickly. Just looking at this, that's a fairly fast response time. It's 100 milliseconds for each of these windows. So it could be about 5 milliseconds response time. The thing is, if the response time is known, then we can calibrate for it. It's kind of interesting that just as this goes up, it starts off kicking back the other way. I'm not sure why. I wonder if it always does that. It's a bit weird. So why would it go? It kind of does it again. All right. Well, anyway, we'll see. I want to trigger when one voltage is bigger than the other. Oh, let's try. I should have a. I've only got one just standard operational amplifier chip in here. I don't remember which one it was. Might be. There is an L293DNE. What is that? I'll just check on this. No, that's something else. That's a 232 interface chip. It's a 7448. L293D. Right, okay, that's not. The other day, I don't know what I did with it. 74LS48, 7448, 232. LM324. Yep, that's the one. It's four operational amplifiers in one package. So this shouldn't take too much effort to get going. So this is the LN324 operational amplifier. Pop it in. Okay, cool. That's in, and the pin out of this thing. VCC is pin 4, 1, 2, 3, 4, so that goes to the positive supply line. Ground is pin 11, which is the opposite side. Okay. And then pins 2 and 3, 2 is the negative, 3 is the positive input, 1 is the output. So this is going to be a little naive, but it's worth trying. Is I'm going to take, well, I don't know, it should be all right. They're high, you know, operational amplifiers have high impedance inputs, so they shouldn't influence the circuit much at all. And I'm really literally want to have it work so that the two voltages are subtracted from each other. And the only question then is, I always say voltages, but it could be that it's current that's based. I don't know. We'll see. That's the big question mark. I'm not really an expert on operational amplifiers yet. So those two inputs are in, and I'm just connecting those two traces to the positive and negative inputs of an operational amplifier, and I'm connecting no resistors. Because of that, the gain of the operational amplifier is in effect practically infinite. I'm probably going to have to change that behavior at some point. I think I'm only connected to trace 2 now, so let's just leave trace 2 in. Let's run. Oh, look at that. And this is actually working, but of limited use. But it is actually working. It's doing what I thought it would do. So that's always encouraging. So what's happening? What's happening is that there are only 2 voltages, more or less, that you're getting out of this. There are positive, you know, the full 5 volts supply line, and we're looking at, let me reduce this is a 1 volt scale. No, wrong button. This is the 1 volt scale. So I've just zeroed it. So there's 0, 1, 2, 3, just under 4 volts. Just about under 4 volts coming in. And so it's sort of smacking all the way up to full or all the way down to 0, because an operational amplifier just left in this way, as I said, has effectively infinite gain. It's like the smallest voltage one way or the other, and it magnifies it to the max. And so that's what we've got here. This is detecting the smallest differences between those 2 traces that you saw earlier. When one is getting a bit above the other, it flips one way, and then it can flip back the other way. But it's so sensitive that it's picking up basically noise. So in order to be useful, I need there to be a certain threshold that it needs to reach for it to actually trigger. And for that I need to put some resistors in there. I suppose I want to. How am I going to make that? What do I really mean? So if one voltage needs to get bigger than a certain amount. Oh no, it's actually the infinite gain thing isn't really a problem. It's just I need to have an offset. I think I can live with the infinite gain, because I really do want it to be either one or the other. Hey there, Michael, how you doing? Good to see you. This is a different thing at the moment to experiment on the bench. I'm working on this circuit that is the camera is having trouble focusing on. on this thing. I'm making an audio detector for a device, an invention to test lag on video games, for which I need, one of the things I need is it needs to be able to detect sounds. So I think if I put an offset, what I'm doing is dragging one of these up or down. How can I put an offset? I can, well, I can use two operational amplifiers. That's probably the easiest way, because I need to use I'm good, thanks, Mike. What I need to do is create an offset on one of these filters, so that I'm adding a voltage to it. This is obviously an operation that I can do with an operational amplifier, but I do need to make sure that it's buffered. That is, the signal from the filter is being fed into a high impedance input that does not affect the balance of this circuit, because if it draws a load, then it's going to affect how the capacitors and resistors and what are behaving. So what I will do is first of all make a buffer circuit. I will draw out what I'm doing here actually. I'm happy that that worked. I thought in theory that would work, and it did. I just disconnected something. What's this? This is the negative apply that. Yeah, okay, pop that back in. Right. So what's going to happen is that in recap, I have my microphone, right, which is just a block diagram, is going into an amplifier. The amplifier is then going into two filter circuits. One filter circuit here. The filter consists of a capacitor and a resistor and a resistor. So this resistor means that it takes time to charge the capacitor from the audio signal, but has been rectified by this. Then when there's no signal, the signal goes down, this capacitor can discharge through this resistor. These two resistors also act like a voltage divider, which is why the voltage dropped. If these were both 1K resistors, then it would halve the voltage in here. But that doesn't really matter. So I've made two of these. One of these has a 100 microfarad capacitor and the other one has a 10 microfarad capacitor. So by doing this, what have we got? We've got a signal that changes according to the noise level, but two of these, one that moves quickly and one that moves slowly. And then what I'm doing right now is that these feed directly into an operational amplifier. So you've got the two like this go into an operational amplifier with a minus and a plus input, and the output is going to the scope. If one of these is a little bit higher than the other, it doesn't matter, at all higher, this output swings all one way. The other way around, it swings all the other way. So you'd expect to see sort of square waves, which we do. But because it's so sensitive, we're basically getting noise. Now what I want to do is change that. First thing is I need to put both of these into, and I have 4 operational amplifiers in there, so I can just use them. What we'll do is feed as the minus, the plus input and the output, and just take the output and feed it straight into the negative. So this is negative feedback on the operational amplifier, which, unless I'm missing something, which is entirely possible because, you know, learning about operational amplifiers is something I'd meant to do and never got around to properly. But I believe this will work as a buffer circuit, so that whatever comes in comes out. It doesn't have any gain, but what it does have is a very high impedance here. So then whatever I connect on this side, yeah, maybe that helped. Whatever I connect on this side is not going to affect this circuit. So I can use 2 of the 4 operational amplifiers like that. But and we can take that. Then after this, we need to do a comparison between these two. So I want to make an offset of 1, probably the fast one, which is this one. So I need to change the offset of this, which I can do by adding a voltage or subtracting a voltage from here. So I suspect, now this is where my lack of knowledge of operational amplifiers means I'm basically guessing, but I will look it up. Something like a voltage divider something like that, so that I basically create a voltage. Yeah, but I need to look this up. But basically create an offset, and then after that offset, I'm going to use all 4. I'm sure that it'd be possible to make it more efficient, but this is the final stage that actually compares the voltages. So what I'm doing is buffering and then offsetting one and then comparing. So this will create a threshold that this will only trigger when the difference between the two is big enough. So let me just do a little bit of a look on here on how to set this up, because I know where I have tried to sort of do things by sort of ear or with operational amplifiers, they never really operated quite the way I expected. So operational amplifier offset circuit. I suppose one way I could do it is I'm overthinking it. I could actually just do a voltage divider. I can do a voltage divider after the buffer. All right, I know that will work. Let me just check the circuit, buffer circuits, make sure that I'm not. Buffer operational amplifier. A buffer amplifier. Come on. So that's an inverting amplifier, but I went. Yeah, it's exactly what I thought. I think I can actually just try. And get there. Did I knock the camera? It's sort of a suspended camera. Right, let's try this. What I'm going to do is dismantle this circuit, this on the op amp circuit here. I'll just take off these two things. I'm taking the fast input. I'm sending that from the fast filter, the output from the fast filter. I'm sending it into the positive input. The negative input I'm sending to the output. I'm going to test each part of this as I make it, following the philosophy as what's the smallest testable change. And we put this on the output, and what I should get, and that's working. So what we have, la. And you see this noise here, it's picking up sound of wind. I could blow on this. Very sensitive to low frequencies. You can just blow on this thing. This is actually it could be used as a air movement meter. You could probably make an alarm system based on the movement of air. If there's a see, it's cool. So it's picking up traffic noise, and it's quite very sensitive. These